Hello there, welcome to our CasADi demonstration here. Installing CasADi nowadays is quite easy. You can just go to the website and locate a zip file or a tar file. On your system you unpack this file and you add the directory to the path. For Python you need to add it to the Python path, for MATLAB it's the MATLAB path. You can see the syntaxes here for Python and here for MATLAB. Let's see if the installation worked. If I ask for the derivative of sine of x, it should say cosine of x, right? And MATLAB agrees with this result. I am giving this presentation in an IPython notebook, so this means I can make some quick changes. For example, here you can see that the chain rule is, of course, correctly applied by CasADi. This demonstration will be about the application of golf. So we consider a golf ball which moves in a plane, vertical plane. So x denotes the horizontal distance traveled by the golf ball and y is the height of the golf ball. And I've devised a bit of an exercise session for this demonstration. Here are some tasks that I want to do with the golf ball ODE, and I'm going to show you how to do this with present CasADi syntax. So yes, the golf ball is described by 4 states, 2 for position and 2 for velocity. We have the gravity vector and we have some aerodynamic drag. So let me define first some constants that are appropriate for a golf ball, and proceed to encoding the right-hand side of the ODE. So conceptually in CasADi you have symbolic primitives, and from these primitives you build expressions. In this case we want a symbolic primitive for the position, which is 2 by 1, so a vector. And for velocity also a 2 by 1 vector. If we want to collect all states together, we can just concatenate these vectors vertically. In Python you have the vertcat command for this. In MATLAB the syntax is a little bit easier even. Now on these matrix expressions you can do all kinds of operations. For example, calculating the norm, the 2 norm. You can see that the 2 norm is here written as a square root of the square of the x part of velocity plus the y part of velocity, as expected. So the right hand side really starts from the velocity, so v, concatenated with this guy. So let's start with the aerodynamic part. And on the second line I add the effect of gravity. So this is just for showing how you can use indices on CasADi expressions. Of course MATLAB is 1 based as always and Python is 0 based. So that's why I have the 3 here and the 4 there. The result of this computation is printed out here or here. So it's a little bit hard to read, but not so much. What you have to look at is this starting parenthesis and this closing one. And there are 4 parts in between these brackets. First you have the x part of velocity, the y part, and then some expressions. And we reuse sub-expressions, and the sub-expressions they get dummy labels, like here add 1 and add 2. And these are encoded earlier in the printout. Okay, so within CasADi these expressions are maintained as a graph structure. So we have a set of nodes basically. So this is the representation of the right hand side. We had velocity along the x direction, velocity along the y. We square the velocities, we add them, we take the square root. So here we end up with a norm and so on. And we compose in the end a new matrix. Okay. Now what can we do with this expression? The end expression, the right hand side. We could, for example, take the Jacobian. So here I ask for a Jacobian of the right-hand side with respect to all the states. So let's see. We expect from the Jacobian that it is a 4 by 4, because the right-hand side is length 4 and the states is length 4. Let's see if MATLAB agrees. Right, I had to print on the printout here on. So here is the full 4 by 4 matrix, and we have some structural zeros here. They are denoted by double zero. You could also ignore the expression itself and just look at the sparsity pattern. So you see that the right-hand side doesn't depend on position, only on velocity. That's why this block is completely structurally zero. There is a second kind of symbolic graph in CasADi, and this is a graph where the nodes are not scalar expressions but matrix expressions. So here before every node was a scalar. If we just replace Sx, which stood for scalar expression, by Mx, then we have the matrix expression type. You can see here that the representation involves less nodes than before, and this is really the core of why Mx should exist. So it's optimized for memory usage, while Sx is a bit greedy on memory but usually much faster. So you can always make a trade-off between these two. So I just started out with replacing Sx by Mx, and the rest is exactly the same. And you can see in the printout or in the graph that, for example, the operation of taking the 2 norm is not rolled out into scalar operations. It's just preserved as one node, which is the norm taking. Okay, so far so good. So what CasADi offers on a high level is efficient symbolics and algorithmic differentiation. So what you see here is another example coming from a single shooting application, and on the x-axis is the number of intervals of single shooting. And then on the y-axis you have the construction time for this expression. And if you use this computational graph model, then the complexity should really be linear in n, and that's what you see happening here with CasADi. Also for AD, if you do efficient algorithmic differentiation, then the order should remain exactly the same. It's still linear. Now you may wonder, why do the other, for example, the computer algebra systems in MATLAB, MuPath, and in Python, SymPy, why do they have a different order? Well, the explanation is a bit simple. Like, a computer algebra system was originally designed to help the human to work out problems on paper. The idea is that it helps doing complicated stuff, and in the end simplifies it in a form that a human is happy to use, a very compact short form. And that is really what is taking all the effort of constructing expressions. But that's not what we do in CasADi. There is not much magic or simplification going on. We just rely on the graph to be efficiently computable and not human-friendly representation. So that's also why the printouts are a bit hard to read. Okay. We now have an expression for the right-hand side, and we have the list of symbolic primitives that define the states. What can we do with this? We can construct a function out of this. Since we're working with the matrix expression type, the mx, we use mx function here. We give the function a name, just a dummy label, and then we have a list of inputs of any length and a list of outputs of any length. In Python it's really a list. In MATLAB you encode it with the cell brackets, the curly brackets. So in our case we have a 4x1 input and a 4x1 output, the right hand side. Okay, so let's evaluate this function numerically. Let's say we want position 0, 0 and then velocity is 5 meters per second. With the vertcat or with the MATLAB structure, you just create a numerical array. Let's wrap it in a list because we're gonna evaluate with a list of inputs, or in MATLAB with a cell array of inputs. So when we do the evaluation, the output is again a list in Python. You can query the first element of the list and you get the numbers there. So this printout that you see here is really a D matrix under the hood. You can always convert it to NumPy array if you want. In MATLAB it's similar. So what is returned is a cell array, and the first entry of the cell is a D matrix. And you can create a simple MATLAB matrix from this by using foo. So the numbers match up. This is the evaluation of the right hand side. Now, whoops. This was nothing special, of course. What is more special is that we can call these functions symbolically. So here I created a new symbol for the angle with which we shoot the golf ball, theta. And I'm gonna construct an initial, I'm gonna construct a state out of this symbolic expression. And then we're gonna feed the symbolic vector into the function. So when we do this, we see in the printout that our function that was defined before, f, is here. So we basically have an expression where f is embedded into the computational graph. And the key is that CasADi does algorithmic differentiation through these functions that are embedded in the computational graph. So if we ask for f out 0, which is of type mx, and we ask for the Jacobian with respect to theta, then we get some complicated expression, and it's actually dense. And 4 by 1 because we're taking derivative with respect to a scalar. Notice in the printout this guy. So f was modified in the process. Well, not modified, a new function has been created by CasADi, which does not only the original f, but also the forward sensitivity. And similar things can happen for the reverse sensitivity. So CasADi just picks forward or reverse or a combination of those to efficiently compute the full Jacobian if you ask for it. And it takes care of, it tries to do a good job of recognizing the sparsity and compacting the number of sweeps of sensitivities that are needed. So the mx function we defined before, previous f, had a list of inputs and a list of outputs. But it's not really defined what the first element of this list means, what the second element means. It's a bit arbitrary and up to the user. So there are a bit of rules for doing like standard forms of input and output. So a standard form for doing a DAE involves, for example, a state, which is defined by the label x here, and involves an ODE output. So that's how you give labels to inputs and outputs. That's basically all. This means that when you call f, or new f, which I called capital now, you don't have to use the list brackets, you can just use a keyword argument. Or in MATLAB syntax you can use a structure. The result of doing a function call with this dictionary or keyword or structure is another dictionary or structure. So you can query it by the usual methods in your favorite programming language. So the numbers that we get out here at the end are exactly the same as before. Okay, first task. This task is just about simulating the flight of the golf ball for 5 seconds. So we start out from some initial launch conditions, initial state, and we have a step size. And now we loop over all the steps in time while integrating. And the integration happens by saying that state the next iteration is the state at the previous plus time step times the right hand side of the ODE evaluated at the previous time step. So big F here is the integrator that we constructed earlier from the nonlinear ODE of the golf ball. If you execute this, we just get a bunch of numbers. We could also use an adaptive step size integrator, a built-in one from CasADi, and the syntax is as follows. You call integrator with some label and some numerical backend. And the third argument is something, a CasADi function that has the I/O scheme of a DAE. So it's this kind of function with annotated inputs and outputs, with dictionaries or structs. So we might as well just put big F here, but here I expanded it into a scalar expression function for speeding up things a bit, but it's not mandatory. The last argument is just a dictionary in Python or a structure in MATLAB options. And the option here is the end time of integration. We want to integrate here over one time step h. What does the I/O scheme look like of the integrator? Well, it has quite a bunch of inputs and outputs, but we're only interested in two. So the one input we're interested in here is the initial state, x0, and the interesting output is the final state. So we can just replace the for loop from before with a call to the integrator instead of manually constructing an explicit Euler. So in this case it will be a higher order scheme. So let's evaluate this, also for MATLAB. And you see the parabola that you expect from a free flight of an object, but they don't match up exactly. Why is this? Because Euler has some discretization error or integration error. CVODS is much more precise. Now, in most cases, the for loop we have here with 50 is quite okay in terms of speed, but sometimes your horizon gets a lot longer. For example, in system identification, it can happen that the number of time intervals is 1,000 or 10,000, 100,000, or even more. And then you can get, you might experience that CasADi becomes a bit slow. It doesn't have to be, so there is a solution. You can use the MapAccum functionality. So out of the integration, you ask for a MapAccum node and a number of repetition, and this is basically a replacement, a verbatim replacement for this for loop. So MapAccum will pass the bucket of the final state to the input of itself repeatedly. Okay, that brings us to task 2. Because in task 1 we had fixed the end time of integration to 5 seconds, but we want to do this eventually for a free end time. So we have to do a time transformation. We can say that time is tau times t, capital T, where tau is a dimensionless time running from 0 to 1. And then we can say to the integrator, just integrate always from 0 to 1, and you yourself do the scaling with capital T, such that you're doing actually free end time integration. But the integrator doesn't need to know about it. So how do we do this in this case? We construct a new VAE function, which I called din here for dynamics. We had the usual states input, but there is an extra one, a parameter. It's something that is kept constant over the integration interval. And in this case, this parameter is the end time. And the right-hand side we multiply with t, as in the transformation formula. And we just, we expand it again and pass it on to an integrator. So let's see what happens here. So this is again some initial states and then a free end time. I can manipulate this and the result will change accordingly. Okay, task 3. We wonder if we give the golf ball an initial kick, where will we end up? So let's say we kick it with a velocity of 35 meters per second and some angle. We can compute the state vector from this. And let's say we're going to simulate for 5 seconds in this case. You will end up quite a lot further, like 105 meters, and a little bit below the ground, which is of course impossible. So what we want to do is find the amount of time we need to reach the ground. So let's take 4. Now we end up above the ground. Let's take 4.5 below the ground. So our goal is to search for the time when the ball reaches the ground, and this is basically an implicit function or a root finding problem. And we can solve this with Newton iterations, Newton steps. So the Newton step scheme involves a derivative, a Jacobian. The Jacobian of the thing we want to make zero with respect to the free tuning parameters we have to make the residual zero. In this case, we can play with the integration time, which was a parameter, and we're interested in the end state. So we take the Jacobian of the end state with respect to time, basically. If you take the Jacobian of a function, you get a new function with one extra output. The one extra output is the Jacobian, and the remainder is just a copy of the previous outputs, such that you have both at the same time. So let's say we start from 5 seconds as an initial guess for the time of flight. We compute the Jacobian of the residual, and we solve a linear system as is given in the formula. If you do this repeatedly, you quite quickly converge to 4.2 seconds. And our ball flies for 92 meters. Now this was manual work. Let's now do it with a built-in functionality. So first we're going to construct an expression for the end state, symbolically dependent on velocity, angle, and time of flight. Like this. Next, we're gonna define a residual function, which can be a generic function with a list of inputs and list of outputs. And it's the y position that we want to make zero, and it's the time of flight t that we can play with. So the first output and first input are really the important ones. The other are helpers. So these two, the initial speed and the angle, are parameters of our problem. And the x position is an extra helper output because we want to know how far we are shooting. So if I evaluate the residual for our guess of 5 seconds, then this number should look familiar. This is the number we try to get to 0. Okay, so once we have the residual function, we can ask CasADi to solve it symbolically. So implicit function is a constructor. Shoot is just a label or a name in this case. Newton is the numerical bucket, so it takes simple Newton steps. And the residual is the residual that we defined. If we now evaluate this, yes, so we get the 92 meters again. So this is the amount of distance that we can cover given this initial guess. You might wonder, how does the shooting distance depend on velocity and theta graphically? So I built a little bit of code to visualize this. Yeah, if you have the time to look in detail here, I use a map node, which is a faster way to compute things. It's again a replacement for a for loop, or a double for loop in this case. So in the plot, yes, in the plot we have on the horizontal axis the shooting speed, and on the vertical axis the angle of the velocity vector at the start. And we can see that we can reach up to 100, scaling is a bit different, up to 150 meters, let's say. Okay, so next task. What is the best angle to shoot to cover a lot of distance? Let's see what happens if we fix our velocity to 35 meters per second, for example, and we sweep over a range of angles going from 30 degrees to 60 degrees. The sweeping we could do with a for loop, and in the for loop calling the shoot function. In this case I used map again to make it a little bit faster, but it's not so important. So what does this graph tell us? Well, it tells us the distance we can cover on the x-axis given some shooting angle. And we see that the top of this semi-parabola is not 35 degrees, as you may expect. This is due to the aerodynamic drag. If there was no drag, then it would be really a parabola. You wouldn't need to integrate, and you would get the optimal solution at 45 degrees analytically. In this case, it's a bit more complicated. So we're gonna try to find the optimal angle now as a function of the initial velocity. Because this graph was only for one specific velocity, we want to do it for all velocities, symbolically. So remember the shoot function. Our shoot function started with a guess for the time of flight and then initial speed and angle, and gave us the time of impact and the shooting distance. And we want to make the derivative of this zero such that we can find the top of the parabola. So we ask CasADi the Jacobian. There's a number 2 here because we're taking the derivative with respect to the angle. And the angle is the third element, which translates to index 2. It's again a root finding problem, so we construct another residual. In this case it's theta that we want to tune, so we want to search the angle. And the thing that needs to be 0 is the Jacobian that we just computed. So we call the Jacobian function symbolically and get the first entry. Then of course we pass the residual to an implicit function with a Newton solver, and we sweep again through some velocities to be able to make a nice plot. So this is for the Python, and for MATLAB coming right up. So the horizontal line was 45 degrees, the reference, and the green one, or the purple one here, defines the tops of these parabolas. Okay, and this is the final task. Final task, we're gonna do a nonlinear problem. We're going to maximize the chance to shoot a hole in one. To solve NLPs in CasADi, you need to bring them in this standard form, with an objective, with a constraint expression, and then lower and upper bounds on this expression. And you can get some simple bounds on decision variables to have more efficiency, if you want. The list of, or the vector of decision variables is just velocity, angle, and shooting time. And we again do the integration function. We call the integration function symbolically to get an end state. There is not really an objective, so we set it to 0. The constraints here are constraints on the end state. So at the end we want to end up at 80 meters, so we set lower and upper bound to 80. We want to hit the ground exactly, so the y position should be 0 exactly. And we also want the velocity to point down to Earth, so that we neglect the other solution, which is at the origin. So we collect a big expression of all constraints. So it's position x and position y, and the velocity of y. Next, we need to create an NLP function, which is just another function with an I/O scheme that is given beforehand, like NLP in, NLP out scheme. So x in this case is all decision variables, f is the objective, and j is the constraints. Next, you construct a solver. And the solver takes the NLP, of course, and the numerical backend and the label. And solver itself is yet again another CasADi function, which we can evaluate with using dictionaries or structures. So it's always the same pattern repeating. Here you can see the IP-opt output, iteration output. So the solution of our, the result of calling the solver is just a dictionary or struct. So if we ask for the decision variables at the solution, and we evaluate the original NLP function with it, then we see indeed we're ending up at 80 meters at 0 height, almost 0, and we have a negative distance pointing to the Earth. So the solution is to shoot 54 meters in this case. Now the solution is not unique, so any small perturbation can make it deviate. I'm not quite sure why this result is not the same, but yeah, solution is not unique. Let's make it unique by creating an objective that tells us a measure of certainty, or rather we want to minimize uncertainty. And uncertainty you can code as encode mathematically as covariance. Covariance is the extension of variance, the scalar thing. So if we take the covariance of a function of an unknown thing, we can, in a linearization, just say that we take the covariance of the unknown thing and left and right multiply with the linearization of our mapping. So we need the sensitivity of our end state, our x position end state, with respect to the free things that we can choose, the velocity and the angle of shooting. So we're after this relationship. And you need a little bit of calculus on paper to obtain exactly the Jacobian that you want here. So let's say that we're not so sure about velocity. We can be 1 meter per second off, and we're not so certain about the angle either. We create a total Jacobian and do the calculus we had on paper, and in the end we get this propagation rule for covariance, and we minimize this uncertainty. Okay, in this case the solution is unique, or at least locally unique. So I'm expecting here 2 times the same result. Yes, 34 meters per second, 34 meters per second. So you see that the best angle to shoot from is not 45, not the optimal angle that brings you as far as possible, but much higher. So you can speculate whether this makes sense. You can also compute the standard deviation of the position where you end up with, and with some probability calculus, you can even compute the chance that you're hitting this hole-in-one. So this is basically concluding our little demonstration of CasADi. Thank you for watching.